All right. Our next presenter is Chanya Metaprayun. Before she comes to the stage, I would like to make an announcement that we forgot earlier. So for all oral presentations, presenters, listen up. There will be an award at the end. During there would be oh. So most outstanding talks from all presentations, whether you're oral presenter or aspiration presenters, you will get a word at the end. So no pressure, have fun. And here's Chanya. Please come up to the stage.
Thank you so much. Hello, my name is Chanya Matapriyun. I'm a rising sophomore at the Audi International School. And today I'll be presenting a project that I did with my group, Samuel, Lakshmi, Prisha, and Irvi, who unfortunately do not live in Texas, so could not be here today, about facial emotion detection using artificial intelligence. We did this project under the guidance of our wonderful mentor, David Babazadeh. So today we're going to go over applications of the project as well as different models and inputs we used until we got our final one, and then finally our results. So of course, facial emotion detection has many applications in the real world, including customer service to analyze customer sentiments, in the automotive industry to detect distracted drivers, and also in education to gauge student engagement. But what we really want to get at here is the medical applications of this technology. So how many of you have heard of Google Glass? Raise your hand. Okay. Yeah, so Google Glass was a pair of glasses developed by Google, and it was designed for autistic individuals, and it would relay the facial emotions of people around the wearer to the wearer. And in the Google Glass trials, it actually helped decrease the severity of the autism of some of the individuals in the trials. So that is definitely an application of this. It can also be used to diagnose or help diagnose preliminary signs of Parkinson's disease by identifying facial masking. So now we're going to get into how we actually developed our models. And so we have this concept of image landmarks, which are basically a set of points on a person's face, and they outline the major facial features of the person. So we're going to play this short video on how our model is detecting this. So we're using this Python library called the dlib model. So you see as we enter the URL of the image, it sort of boxes around the face. And then next we detect the facial landmarks. So these are 68 major points on the face that are detected with this model. And then so what we do with these points, we take the distances between each pair of them and we store them in an array. And this is our input for our model. This is helpful because, for example, if the eyebrows are really high compared to the eyes, it might indicate some feeling of surprise. If they're really scrunched up, it might indicate anger. So it helps us detect the emotions. And then so we input this into our simple classification algorithms, our KNN, our LR, and our DT. So for our first model, which was our k-nearest neighbors classifier, it classified images according to the ones that had similar characteristics to it that had an accuracy of 48%. For our second model, it used a logistic function to classify our emotions, and that had an accuracy of 53%. And our third model had a series of conditions to see if the image satisfied it or not, and that had an accuracy of 43%. So as you can see, this is still not as great as human accuracy, which is 65%. So we still want a better model. So what we did next is we tried out artificial neural networks. So how these work, they're basically made of units called perceptrons, which are represented by the white circles on the image. So these work like a biological neuron. It takes in an input, it weights the input, and it relays an output. And when you put multiple layers of these perceptrons together, like we did on the MLP, or multi-layer perceptron, it ends up being able to process more complex data. And has a more depth of its response. Next, we have the CNN, or convolutional neural network. It's basically also made of multiple layers of perceptrons, but this time it's detecting patterns in a 2D image. So for MLP model, we put in two inputs. One was the actual grayscale values of the pixels in the image, and one was the distances between facial landmarks that we talked about previously. So for our pixel array input model, it had a testing accuracy of 45%. One downside of this model is that by inputting this pixel array, we actually lost the 2D nature of the image. So that's why the accuracy is not as high. Our second model was putting in the distances between facial landmarks, and that had an accuracy of 53%. However, we still wanted a better model, so we tried out the CNN. And I'm going to go into depth on this one because this was the one that worked. So first, we initialized our model. Then we added a convolutional layer, which detects patterns within the image, like edges. Next, we normalized our images, which allows the grayscale values of each image to be consistent with each other. Then we did a pooling layer, which captured important features of the image, and then we did dropout, which allows our model to actually learn the connections we want it to learn without actually memorizing our data we trained it on. And in the GIF above, you can see how this is working. So we have this sliding kernel that represents basically the edges or patterns that our model wants to detect. So if we're creating a CNN model from scratch, this kernel values are randomized. However, we actually took some kernel values that had actually been trained on images of animals for our other CNN model, which is called the VGG. So what this did, it might not seem helpful, but it basically provided a baseline for us to detect edges and such without having to start from scratch with randomized kernel values. And so this is what our CNN model's accuracy was like. Our randomized kernel values CNN had an accuracy of 64%, and our VGG model had an accuracy of 70%. So as you can see, our VGG model accuracy exceeded the human accuracy on this data set. So here's a summary of our results. The blue line is the VGG model. The other should be straightforward, and the straight lines represent human accuracy and chance respectively. Yeah, so I wanted to end by talking about the significance of facial emotion detection again. Not only can it be used for autism and Parkinson's, it can also be applied in a general medical setting to better foster interactions between patients and medical staff, and also to see how patients are responding to treatments or medications that they might be taking or undergoing. Oh, there is supposed to be a thank you slide. But anyways, yeah, thank you for listening, and I will open the floor to the audience for questions.
Well, thank you, Chanya. Questions from the audience? Yes.
Hello. So I would just like to ask that for the AI program, does it increase in accuracy if you also increase the computing power allocated to it?
So the increase in accuracy comes by adding more convolutional layers, basically more perceptrons to train our model, which can be made possible by more computing power. So yeah.
All right.
Do you think it would train faster if you added the distances along with the CNN model? Because CNN, like, it takes a kernel each time, so it's kind of slow to like interpret distances. So if you like add the distances as like a separate variable, do you think it would train faster?
Yeah, so CNN is specifically suited for interpreting images. So you have to put in a 2D array of image pixels. I guess that could be another factor that we could factor in, and it could definitely help.
Are there any limitations to like what a face can look like? For example, if they have like a deformity on their nose or if their eyebrows are shaped, does that like influence, does the model predict worse when there are facial differences?
Yes, I would believe so. It predicts according to the data it's trained on, and I don't believe the data it was trained on had any of those features.
Great.
How much training data did you use and where did you get it from?
Oh yeah, so we use this data set. It's called the FVR 2013 data set. So it's a data set of grayscale images of 48 by 48 pixels. And then so we split our data set into training and testing. So 90% of it was for training and 10% of it was to test if it can respond to data it wasn't trained on.
All right. We're going to move on, but during the break or lunchtime poster sessions, please feel free to find each other and ask more questions. So we encourage you guys to get connected as well. And thank you very much, Chanya. That was great. And if you